here's where I give my little vector speech. Okay? Some of you are in AP Physics, some of you are not. I don't know who is and who's not, and I don't really care. I'm going to just teach this like you don't know anything about vectors. This is page 311, something like that. My caution to you on this is two different things. Number one, some of you in physics have already decided I'm not good at vectors because I wasn't good at them in physics. Therefore, I'm not going to be good at the vectors you're telling me about right now. So you're already mentally shutting down on me for the rest of the chapter. Please don't do that.
Too late.
Second issue that I've actually run into on the vectors chapter is some of you are like, heck, I'm really good at those vectors from physics, so I'm going to be great at this and I don't have to pay attention. Not true. We do vectors differently than physics does vectors. Because when you do vectors, you don't have law of sines and cosines to solve. I've just taught you that, and that's what we're using to solve. So the setup is entirely different. Okay? Some things will transfer. Some things will. However, if you refuse to pay attention to how I teach you how to set up word problems with vectors, and you think you're going to be able to do them like your physics ones, you're going to get almost every problem wrong on your word problems. I'm just telling you up front because I've seen really smart people who are very good at math and usually get A's and over 100s on my test bomb it because they refused and said, I'm just going to do the physics way. Okay, have fun. Doesn't always transfer. I'm teaching you a different way to do it because the point is you learned one way with one method and you're going to learn another method with me. That's just going to be how it goes. Also, my other caution is if you at all can help it, do not miss Monday's class.
What's on Monday?
We are learning about compass directions and angles. And I'm spending an entire day talking about it to beat it into your heads. And if you miss it, it is not pretty. I'm just saying. There will be the video this time, which will help. But if you can all help it, do not miss that class. I just be upfront with it. Okay? Now, today is the basics of vectors, which is not very difficult at all. A little bit of drawing, a little bit of algebra, nothing very complicated. A little bit of vocabulary. Okay? But we're going to build some of this stuff as we go. So vectors have two parts to them. The two important parts about vectors are they have a magnitude, which is the length of the vector. They also have a direction, which is an angle. Okay? You can write vectors two different ways. You can write them using a magnitude and direction. You can also write them in what's called component form, which we will talk about. And next class, we're also going to be talking about how to transfer between the two. Okay? So the length of the arrow that you see on any of these things represents the magnitude, which is the length of the vector. The arrowhead itself indicates the direction. Okay? Now, this little box here, compass direction, that's what we're spending the majority of our next class on. It is measured in degrees from north, clockwise. Okay, so here is where, this is what I'm telling you about next class will be important. This direction that we're measuring here starts here and goes around in a clockwise direction. Here's the issue. Your calculator does not talk compass direction. Your calculator talks unit circles. Okay? If you remember the unit circle, it started here going the opposite direction. Yay. Correct? So what we have to learn is how to take a compass direction, draw it in a picture, transfer it into a unit circle for the purpose of our calculators. It is not overly difficult to do, but that's why I say don't miss next class. Because if you have to do it on your own, it is kind of difficult. Okay? I've got good practice at this point. Okay? However, what we say about this vector then is that it has a magnitude of 5, because notice it's labeled with a length of 5 there. The compass direction is counted from north. Notice they only tell you it's 20 degrees below the east side there. So we have to think in our heads, a full quadrant is how many degrees? 90 plus an extra 20 gives me how many? 110. But that is what we're going to be talking about the majority of next class, dealing with the angles and how to find them. Literally, we're going to take 10 practice problems, spend the majority of class just saying, if I give you a compass direction, draw it, switch it to a unit circle, and go in between all the forms so that we're comfortable by the end of the class. Okay? We consider two vectors equal if two things are true about them. They have the same magnitude and same direction. So notice in that picture there in your notes, those two vectors are not starting and ending in the same location. They are, however, considered to be equal. Where vectors start and end is not as important as their direction and magnitude. So we call them equal when they have the same direction and magnitude, doesn't matter their position, starting and ending. Okay? So what we're going to see then with vectors is that we can do several operations, which is how we're spending our day today. We can add them, we can subtract them, and we can do scalar multiplication of them. Scalar multiplication is just multiplication by a number. There's two different ways to do this. Okay, your notes here are the geometric way. Geometric is translated really in this case as the visual method. This is drawing out your vectors and finding the answer from a drawing. Most of us will choose not to do this if I actually ask you to do two vectors and add them together, because the algebraic way will make much more sense. That's fine. However, this method here that we're using to draw them, called the tip-to-tail method, that's what we're going to use for word problems. So just being able to draw the vectors here and know how to set them up is the important skill. Less important is knowing how to add them using the drawing. We'll just do both together, really. Okay? So the tip-to-tail method basically says if I'm doing anything with vectors, multiple vectors, we start with the first one. We draw the first one. Typically, we start at the origin if they give us an XY coordinate plane. You start with the first one. When you do something with the second one, you start it where the first one ended. Okay, so we're going to see that. And we're also going to talk about something called the resultant vector, which is the answer. Okay, the resultant vector just means the answer. Okay, it's drawn from the first tail to the last tip. This will make a lot more sense on the next page when we do an example. Okay, on the next page for us, we have two vectors drawn here. Notice these are not on an XY coordinate plane because it doesn't necessarily matter where they start and end. What matters is their direction. For this, we are going to talk about their component form. Component form is an X direction and a Y direction written in these little pointed brackets. You must write these in the brackets as they look, because if you put them in parentheses, I'm going to assume you're talking about a point, not a vector, and that's different. Okay? So these vectors U and V, these are just given to us so that we can do the following examples. So anywhere they refer to vector U, they're referring to this vector U on this picture. Anywhere they refer to vector V, they're referring to that vector V. So before we get started on them, we have to define what are vector U and V in component form. To do that, all you have to do is count. From the ending point or the beginning point of vector U to the ending point, which is the arrow. So when I count vector U here, I'm saying, okay, if I start there and count to the arrow, first I count the X direction. I have to count how many places to the right. If I'm counting from here to here. 4 to the right, that is your X direction. Positive 4 because on your coordinate plane, to the right is positive, to the left is negative. Then I count how many blocks down? 8. Down in the Y direction should be what? Negative. So that is the component form of U that we're going to use. Every time we draw U, no matter where we start it, we're going to go right 4 and down 8. Doesn't matter where you start, doesn't matter where you end, as long as from start to finish you go right 4 down 8. Same thing for vector V. The hard thing with this is remembering to count the X direction first because it looks a lot like slope to us. So we want to count the up and down direction first. So just be careful with that. So from vector V, I'm counting right how many and up how many? Up 2, which will be our Y component. Right how many? 6. Okay? So once we know the component form, it makes it easy to add or subtract these together. I'm going to show you both the algebraic and the geometric on each of these so that you can just see them together and understand how they work. Geometric means we're drawing it. So I'm going to skip 1 for a minute because adding them makes more sense to begin with than the scalar multiplication does. In question 2 here, it starts with vector U. That means anywhere on this picture we need to start by drawing our vector U. So I'm just going to start here. Doesn't really matter. Again, you don't have to start in the same place. What matters is that to draw vector U, you go right 4 and down 8 and draw yourself an arrow. So I count right 4, down 2, 4, 6, 8, and I draw myself an arrow to show my vector U. If I would like to draw my vector v now, and we're adding it to that comes second, the tip to tail method says that from where I've just ended vector u at the arrow, this is where I start vector v. So vector v starts right here where I finished. Vector v, we said we count which way? Over 6 and up 2. So now I draw vector v starting where I ended vector u and ending over here. What we call the resultant vector, we draw from the original starting point to the final ending point. So that means I start way back where I started vector u, and I draw my resultant vector going all the way to where I just ended vector v. That vector is my answer vector. All you have to do to find your answer geometrically is count, just like we counted for vector u and vector v. If I count, starting here and going all the way over to where I just drew the arrow, we would count right how many? 10. And down how many? 6. Okay, literally just counting blocks from start to finish. Now that can be confirmed algebraically, and this is what I mean by most of you will not want to draw a picture for this. Because the easier way to do this is to take vector u, which we said was 4, -8, add it to vector v, which was 6, 2, and just add the separate components together. 4 plus 6 gives us this 10. -8 plus 2 gives us this -6. Same answer, but we would do it algebraically if we had the choice. The reason I show you the geometric way, like I said, is for the word problems, so that we can draw one vector, draw a second vector, and find the resultant. Because if you notice, what shape does this make here? A triangle. And guess what we're going to use to solve the sides of it? Law of sines and law of cosines. It's coming back to us. That's not going away. So that's where they're going to connect together. All right? So we're just going to do a couple more examples of doing these so that you can do them on your own, and then I'll finish up with a couple formulas. If you do scalar multiplication, that's multiplication by just a number. That's that 2 out front. 2u literally means we're putting 2 vector u's together. So I start with 1 vector u. Again, starting wherever I feel like it, but counting right 4 and down 2, 4, 6, 8. So I start with 1 vector u. I begin my second vector u where my first vector u did what? Ended. So I start right here where I finished, and I count right 4, down 2, 4, 6, 8 again. Okay. So my second vector u, I think I just went too far on that one. 2, 4, 6, 8. There we go. Second vector u goes from there to there. This is why this one doesn't make a whole lot of sense to do first. The resultant vector goes from the original starting point to the final ending point, which means my resultant vector for this one is this whole thing. Okay? But again, if you didn't want to count how far to the right and how far down this went to find your resultant vector, we could just say 2 distributed to vector u from above. You would distribute to both parts, your x and your y component, and that would give you your resultant vector, which would be what? 8, -16. And that should be the same amount of blocks that you'd count, provided that you drew it right. Right 8, down 16. Okay?
Okay.
All right, one more on this page. We'll do one on the next page, and then we'll finish up with a couple of formulas you need to know, and that will be it. On 3, if you're to do subtraction, the only difference is that instead of when you add them, you do vector u and then vector v correctly as they're written, you do the opposite of whichever one you're subtracting. So what that means is, for question 3 down here, we'll just do part A. If I'm to subtract u minus v, I start with vector u. We've discussed how to do that. We draw vector u wherever we feel like, as long as we go right 4, down 2, 4, 6, 8. If I would like to subtract vector v, that just means I do the opposite of the directions that I'm given for vector v. So vector v was supposed to be right 6, up 2. If I'm subtracting it, I'm just going to go where? Left 6 and down 2. Of course, starting vector v where I ended vector u, so that I can do that tip-to-tail method, which means my resultant vector goes from the original place I started u to the final place I ended v, which means I draw my resultant vector in here. Again, you can find your resultant vector in 2 different ways. If you want to count, you can say that vector I would go left 2 and down 10, I think. Or what could we do algebraically? Take vector u and just subtract the components of vector v, which means I would be doing 4 minus 6, like we said, left 2, negative 2. Negative 8 minus 2 gives me negative 10 or down 10. Same answer, different ways. Some of you will like both drawing and doing the algebraic because you can kind of confirm your answer and make sure you're right. But some of you will find that too much work. Totally fine. All right, the last one we're going to do is on the following page. If you will flip over, we're going to look at question 4. The last one of these kind. Because once you've drawn a couple of them, you're kind of good. All right. If you flip over, we're going to do 4b. I'd like for you to take a minute on your own paper. We're still using the same vector u and vector v from the previous page. So take a minute on your own paper. Draw out, remember we've already talked what 2u looks like. That was part A on the previous page, so you know how to do 2u. And do a subtraction of half of v. And see if you can figure out what the resultant vector will be. It's just on the previous page. Vector u was 4, negative 8. Vector v was 6, 2. So we're doing 4b on your own paper. All right, once you're done, check your answer against mine. Either way you're drawing this, remember 2u is literally 2 vector u's put together, end to end. Minus half of v means you're literally just subtracting half of what v would be. So you can take 6, 2, divide by 2. Or you can get your answer the algebraic way, which is what I showed out there to the side. If you're multiplying, you are distributing to both components, but remember when you're adding and subtracting, you're just adding and subtracting the x's and then the y's separately. Any issues with the drawing and the vector so far? If there is something that asks specifically for you to draw it on a quiz, you're going to have to do it. But I typically let it, I don't remember ever asking on a test or a quiz and saying you must draw this out. The word problems you're going to have to, otherwise they're going to be completely screwy. But I don't usually ask you to do it that way. No. All right, 2 other things to talk about real briefly here. One is magnitude. There's a formula to find it. Okay, first and foremost, please note the notation here for magnitude. What does that look like on either side of the vector? It looks like absolute value bars. In vector chapter, it is not absolute value. It's asking you to find the magnitude or the length. Secondly, the magnitude formula, this is a modified version of the distance formula. You know where you do x2 minus x1 squared, y2 minus y1 squared. Basically, the x and the y from your components, you've already done the subtraction to find the distance between them. That's what our counting is. So that's why you have this magnitude formula to find the length of it. Okay? So if I was to do example 5 down below. Now first, I guarantee you when we get to the quiz on this in a couple days, it'll be either next week or the following. Can't remember where it falls. Some of you will look at this and say, how do I find the absolute value of that vector? Okay, we've been over this. That is magnitude. You need to know what it means in this context, because I'm not going to say in words, find the magnitude of that. You need to know the notation for it. Okay? In order to find the magnitude of vector u, I need to first find its component form. We know how to find that. Let's review. How do I count to find the component form of u? count over how many it goes, and then down how many it goes if I'm counting. Good thing I went far enough on that. All right, so if I count over, I believe in this one I'm counting right 11 and down 8. Once I have component form, all it is a matter of plugging it into that formula to find the magnitude. I always, always, always want simplified radical form and not a decimal for this. So when I find the magnitude of vector u, I'm simply doing the square root of the x component squared plus the y component squared. Remember, when we square negative numbers, we must put them in parentheses, please. Otherwise, you will get the wrong answer. Okay? If I do 11 squared plus 8 squared, it gives me the square root of 185. I would simplify that if I could, but I can't, so I'm going to leave it there. Okay? We always want the simplified radical form. So just remember, if a perfect square goes into it, you can square root it and take it out front. Okay? Very last thing we're going to do is skip past this next page and finish up with one thing on algebraic. We've already done algebraic adding and subtracting as we did the geometric, so I'm not going to go over those again. We've already done add the components together when we were doing that with geometric. I do just want to talk about another way to find component form. Noticing the example 1 here. Are A and B vectors or are they points? How do I know? Okay, first, it doesn't have the arrows over the letters. Second, what's around the numbers? Parentheses, which means points. They have to be the pointy things to be vectors. Okay? You can have a coordinate plane here. Notice we have like an origin and an x and a y axis. And you can define a vector by a starting and an ending point. How do I know which one's my starting point? A. Why? Because if I look at this vector notation, it starts with A and goes to B. So that means when I draw this, I start at point A, the point over 4 up to 4, 6, 7. Here's point A. And I draw my vector to point B, which is negative 4 up 3. Of course, I can always choose to draw this, count, and find component form. If I count how far it goes to the left, it would be left 8 and down 4. I can count to find component form. However, let's just say, like most of us, we would not want a graph if I didn't have to. Okay? If I give you points A and B, you may also use this formula right here to find component form. X2 and Y2 are your ending point, which is which point in this case? A or B? B. And X1 and Y1 would be my starting point, which would be point A. So if I was to do that to find component form, I would do negative 4 minus 4 for my X, and I would do 3 minus 7 for my Y using my points A and B up here. That's a whole lot like slope, only it's just not in a fraction form. It's the Y's and the X's separately. Either way, though, if you do negative 4 minus 4, you still get that negative 8. 3 minus 7 still gives me that negative 4. So you just have two options to find component form. You can subtract them on a piece of paper, or you can count them on a graph.
Do we have this formula?
We're going to talk about formulas as we get towards the test. I have yet to decide. Some of it depends on what they give you for dual credit. So I got to figure that out. They haven't sent me the formula sheet yet. I try to go with what they get. Real quick, last thing we'll do, just because I'm not going to be able to do the next example, magnitude of V. Okay, well, we just found component form of it. How do you find magnitude of it? We just went over it. Square root of negative 8 squared plus negative 4 squared. Always simplified radical form. So 8 squared is 64, 4 squared is 16. If I add them together, I get square root of 80. Can I simplify the square root of 80? Yes. 80 divides into 16 and 5. Square root of 16 is what? 4 root 5 would be my magnitude for that. Like I said, next class, part of what we're doing is working more with this component form, as well as magnitude and direction and how to switch between them. Okay? Homework for these two sections, 2 different parts to it. Over on the worksheet titled Geometric Representation of Vectors, this is page 329, I think.
Yeah.
We are doing questions 1 through 6. Now, on 1 through 6, they are all using these vectors given to you right there in that picture. So before you ever get started on 1 through 6, take a minute and just write down the direct or the component forms for U, V, and W so that you don't have to refer back to it a million times. On algebraic representation of vectors, we're doing 1 through 5. Okay? But the next class is the real important one with compass directions that we have to talk about all that. Yay. Okay?